who's faculty at the University of Oregon, and she'll be telling us about BBN constraints on ultralight scalar dark matter. So without further ado,
great, thank you. So is this size text okay for the people in the back? You can, and this is probably too a little larger than this.
That BBN is
the BBN is good. Yes. Okay, so I will try to.
Also, my eyesight is very bad, so maybe.
I think yeah. So you're a good test.
Maybe just sit close.
Okay, cool. So I wanted to tell you all today about some work. So it's a combination of two works. So the first one was a paper that came out in 2020 that I wrote with Sergei Sibirikov, who's currently at PI and McMaster, Philip Sorensen, who's finishing up his PhD at Daisy, and he's going to move to Padova in the fall, and myself, and so you can find that here. And some work in progress with my grad student Tom Bully at Oregon, and Philip, which is kind of extending the work that Sergei, Philip, and I did earlier. And so the goal of this work was to kind of understand how ultralight scalar dark matter would affect BBN and what kind of constraints we could set on these types of models. So let's see, to begin with, my iPad. See if I can draw this picture. So what am I talking about? So if I draw, so this is a bad rendition of these plots that you see from NASA, where this is today. This is supposed to be the history of our universe. I
think you have a period of matter down there.
Yeah, I think there's a lot of stuff going on here, and this is, who knows what's going on here. So here's today, and prior to today, we had a period of structure formation. And then before that, we had the CMB, so I think we'll hear quite a lot about this tomorrow from Kim. And before that, we had have Big Bang nucleosynthesis. So as we know, we can measure time with temperature and energy. And so today we are looking at things around 2.3 times 10 to the minus 13. All these are going to be in GeV, so quite low energy. At structure formation, we're probing energies of around 10 to the minus 12 GeV. At CMB, it's 3 times 10 to the minus 10. And at BBN, we're about 0.1 GeV. Okay? So we see that there's a huge expanse of that we span in energy. And what's really kind of remarkable, so I'm going to focus here, what's really kind of remarkable is if we take the physics that we know today, like the Standard Model with all the Standard Model interactions, the weak, the strong E&M interactions, apply all that microphysics at BBN, we get really remarkable agreement with the observed abundances of these primordial elements today. So a consequence of that then is that any small modification we make at BBN then propagates to now, and because we're spanning such a large range of energy, any small change becomes a fairly large change at today. So that's kind of what I wanted to investigate in this talk. Okay, so what is BBN? So BBN is where we form the primordial elements, and so which elements am I talking about here? So we have things like helium-4, deuterium, which I use D for, lithium-7, and helium-3. And the one I want to focus on today is helium-4 because this is kind of the simplest one to calculate and to predict the abundances. I learned recently, I guess Michele, maybe you know because this was a GGI talk, that apparently the lithium problem is no longer a problem. So that's kind of nice because I didn't work on it, and now I don't have to think about it anymore. So with lithium-7, so the lithium-7 problem was that the predictions of BBN predicted a higher abundance of lithium-7 than what we observed today. And there was a theory that the lithium-7 that we see, I think, in metal poor stars is the lithium that was produced at BBN, and there was no change in the amount of lithium. And part of the reason for this was because there was also observation of lithium-6, which I think is easier to disrupt. And so the theory was, because we see lithium-6, which is easier to destroy, there could not have been any process that also get rid of lithium-7. And so all the lithium-7 we see was primordial, and it was the same amount as what it was in BBN. And I think Keith Olives and Brian Fields had a paper in April saying, one, the observations of lithium-6 are no longer there, and it seems that there are processes in stars that can destroy lithium-7, and that explains why there's less lithium-7 than what you would predict in BBN. So I thought, yeah, that was kind of because I'm just growing up as a physicist, you always hear the lithium problem, and it seems like maybe it's not such a big problem. So, yeah, I don't know if everybody agrees with that, and I guess there's a recorded talk from GGI by Olive or Fields, I don't remember which one.
The other one.
Fields.
Yeah.
Brian Fields. Okay.
There was also a new physics forum talk. That was on the agenda.
Okay.
Yeah, we do have one recorded talk on the website as well.
Okay, so yeah, so if you want to learn more about the lithium potential non-problem, there's a few recorded talks about that. Okay, so I won't talk about lithium at all today. Okay, so I'm going to focus on this one because this is kind of the simplest to calculate. And so to start off with, I wanted to walk through the steps of how do we kind of predict the amount of helium-4 that we have. So let's start at high temperatures. So let's look at temperatures above an MeV. So when we're above an MeV, we have the weak interactions that are on. And these weak interactions keep neutrons and protons in equilibrium, in thermal equilibrium. So we have weak interactions. So keep neutrons and protons in thermal equilibrium. So you have things like neutrons going to protons plus C minus plus nu bar, nu plus n going into P plus E minus, and then E plus E plus nu bar. Okay, and so through these processes, then we can calculate what is the ratio of the number of neutrons to protons, and we get that the ratio is given by the mass difference between neutrons and protons over the temperature. And so you see this ratio drops exponentially. Okay. So this process is going on, but while this is going on, our universe is expanding. So at some point, they'll turn off. So we have basically two things going on here. So I have temperature. Now temperature is decreasing to the right, decreases. And I have some rates. So I have the weak interactions, which go like something like this. And these scale like temperature to the fifth, like G Fermi, T to the fifth. And of course, so the universe is expanding, and Hubble goes like T squared. So we have something that looks like this. So this is Hubble, which scales like G star, Gn, T squared. And at this point here is where I'm going to call weak freeze out. And so this is when these weak interactions are slower than Hubble and they stop. So we freeze out the number of neutrons with respect to protons. We call this T freeze out. And you can do a simple comparison of these two to figure out at what temperature does this happen. So I just want these two rates to be equal. So if you go and do that, this is just some simple algebra. You get the freeze out time is related to number of effective degrees of freedom, Gn, over the Fermi constant to the fourth, all raised to the 1/6. And if you go and plug in the numbers, this gives you about 1 MeV. Okay? So this is why I wanted to start above an MeV when all these processes were on. And once I hit an MeV, these stop. Okay? And so if you go and plug this freeze out time temperature into this ratio, so N over P at T freeze out, you get about 1/6. Okay. However, we know that partly because of this process here, neutrons are not stable, so they'll continue to decay. So we have some neutron decay. You actually end up with about one neutron for every seven protons. Okay, so now once we have this collection of neutrons and protons, so 1 neutron for every 7 protons, what happens? Well, you have, let's say, there's a proton, there's a neutron. They come together and they form deuterium. And there's a period called the deuterium bottleneck, which is that you form deuterium, but because we also have this photon bath that our deuterium is sitting in, and at these temperatures, the exponential tail of the photons are energetic enough, they have higher energy than the deuterium binding energy. So even though you can form deuterium, you still have these photons out that will break it up. And so you keep having this process of forming deuterium and then it getting broken up by the photons until the universe cools off enough, and this is what we call the deuterium bottleneck. But once that happens, then things happen quite quickly. So we have deuterium that then goes into tritium, which is two ends here. And then this goes into helium. So we have P, and N. This is tritium, this is deuterium. Okay. And this is quite stable. This helium is, I don't know if you can see, it's just the cartoon here, nothing too profound. But this helium is quite stable, so all of the free neutrons end up in helium, and in particular this helium-4. Okay. So you can get then the final abundance. If I write here, I guess people cannot see.
Sorry, can I ask a silly question?
Yeah.
What makes the second neutron, isn't deuterium already quite stable by itself? Why does it want to attract it?
This one, why does it want to go?
To go all the way to helium?
I guess this has that's a good question.
Meaning it's the middle thing. Why does the neutron want to become tritium, which is an unstable?
Why not just go straight from here here to here?
Why doesn't stay in deuterium?
This is more bound.
Yeah.
Yeah, but he has to go through.
So he has to go through deuterium.
Bound, or no, maybe I'm wrong.
But I think you can also go directly.
Yeah, it can also go directly into helium. But the point is that.
This is very fast than it's different.
But I think the neutrons want to, if they had a will, they would want to be in helium, helium-4.
I think deuterium is less stable compared to helium. I think
It's yeah. So there's these plots that you can see of the abundance versus time. Yeah, it's more. Yeah, it's more.
This is the reason why it can be broken when you update the
But there is. I mean, we do have a primordial abundance of deuterium too. So.
You don't break the primordial remember. For example, you won't have the turning from the start, and it will always be broken.
Right, okay.
So yeah, good. Really good. Okay, so. But the question was, if I write down here, I guess people in the back cannot see on this row.
By the way, we would start primordial abundance of issue. It's just that we know how to predict it, but we know.
I think we can't detect it. Yeah, we don't know how to. Even helium-3, I think we don't know how to detect. Okay, so maybe I just come over here. What's this? Okay, so we've established that we have all these neutrons that end up in helium-4. So how much helium-4 do we have? So helium-4 is given by Yp by convention. And this abundance is given by 2 times the ratio of the number of neutrons to protons divided by 1 plus n over p. I go and plug in 1 over 7. You get that this is about 0.25. So about a quarter of the abundance is by helium-4, and this is actually quite close to what we measure, and also quite close to what you would calculate with more sophisticated techniques. So pretty good for this really rough cartoon picture. So what are the more exact numbers? These actually might be a little out of date, so I should actually check. But the theory prediction, like doing a more thorough calculation, gives you 0.24709 plus or minus 0.00025. So quite small error bars here. And the experimentally observed value is 0.245 plus or minus 0.003. Okay. So in good agreement with each other. So the question I have then is how much new physics, one, could you hide here, or how much can you constrain new physics? Because as I said earlier, any small modification to physics at early times will affect this number. And this is quite constrained, so you can set some fairly strong constraints on new physics.
How to measure the helium abundance?
Sorry?
How to measure the helium abundance?
Yeah, it's looking at spectra of stars. I think that's about as detailed as I can get.
Measure better.
No, just one, first of all, I said something wrong before because tritium decays. So
Yeah, so
so
tritium.
is helium-3 the one that I was talking about?
Okay.
So,
Yeah.
this is,
So tritium you can't detect because it's not there.
It's gone.
Yeah.
It's just gone.
Whereas helium-3 is helium-3 is there, but it's harder to detect. Helium-4 you can.
Helium-3, you have a primordial prediction, but that is super hard to get it.
Detect.
Tritium is unstable.
Tritium is unstable, so maybe the diagram should have like 2 protons and a neutron, not 2 protons, 1 proton and 2 neutrons.
Yeah.
It's a very fast process, right? So I think it's cool. Immediately go to
Yeah, there is possible.
There is possible.
It's
possible.
It's
Possible. I totally agree. But just to
Okay. Yeah. So no tritium.
So sorry about that.
Yeah.
For the question you asked, I mean, you measure helium, primordial helium, doing a linear regression from the gas in metal pool galaxies. Okay, so basically you observe spectroscopically in the near infrared the metallicity. You do a plot like abundance of helium versus metallicity. You collect like 50, 60 objects, and on the basis of the of the metallicity versus the abundance, you do a sort of inference of the limit of zero metallicity. That's the way you do it. I don't know if it's clear, but I mean.
Yeah.
Isn't deuterium measured much better than before? If you want to use
Deuterium is better than because you do better spectroscopy in quasars. That's it.
Is there some also quasars for helium-4 as well, though? Or only?
I think there are some.
So there's a few different techniques.
I don't know why you're not an astrophysicist. It's out there, I guess.
I was just asking for constraining constraining new physics from BBN.
The best measurement is BBN. It's not BBN. Helium is a little bit.
Yeah, there's more wiggle
It's a
room.
trade-off because theoretically
You predict helium-4 better, yeah. But so it's harder to make a prediction for deuterium because there's other nuclear reactions that are involved. And so actually we looked at, in the first paper, we looked at deuterium and it gave a slightly weaker bound than helium-4, even if the observation is more accurate. So, great. Yeah. Okay, so we have this, we can then compare what is the difference between the theory and the experiment. So I'm going to call this delta yp over yp. And this is something quite small. It's about -8 times 10 to the minus 3. Okay. And what's involved in just theoretically, how can I change the helium-4 abundance? Well, there's two parts I can change. I can change the number of neutrons that I have, like this neutron-proton ratio at weak freeze-out. So I'm going to call this delta xn sub w, w for weak. This is the neutron abundance. Or I can also change things that involve the neutron decay. Okay. dA, gamma n. So now I've switched into scale factor, okay, because it's a bit easier to calculate here. Okay. So I can either change predictions for the neutron abundance or change predictions about the neutron decay. So the reason why, just to kind of recap, the reason why I want to focus on helium-4 is because we see it only depends on this neutron-proton ratio, which then in turn depends on a few things, but for example, the mass difference between neutrons and protons, the weak interactions, including the neutron decay.
Can you say more about how you determine the delta YP over YP? Is it just the difference between the two?
Yeah, it's the difference and then the errors.
So that's not like a confidence limit, it's just an actual like target you're trying to make them in harmony, or?
Yeah, so it's saying if I have some modification at delta YP, I'm allowed to wiggle. There's a plus and minus.
We're taking into account.
Yeah, there's actually this is 0.1 to 83. And then we do a 2 sigma, plus or minus 2 times this.
That uncertainty is more significant
Yeah.
than the central value.
Yeah, I mean, this is basically 0.
Right.
Okay.
This one theory, the one theory being so precise is still sort of puzzled over.
Why?
I think mainly just because I would have thought that the baryon photon ratio is not known nearly to this precision in some way. But I may be wrong.
I think it's.
So you are just surprised about the precision?
Yeah, this precision. Because it depends on the baryon photon ratio.
Maybe there's a saturation value of photons, like as long as you have more than a certain amount, like it will dissociate the neutron anyway.
No, but we know from these BBN plots, right? It's just it's sort of a linear rising function.
Yeah, I think you're thinking about this like
In order to hold that error, it's a Gaussian distribution from the Planck analysis or another.
But it really is, it's that.
I mean, within lambda CDM, yes, otherwise not. As soon as you move from lambda CDM,
Yeah.
you're right.
So, okay, so then the CDM, with an effect,
Yeah.
going forward.
And in fact, I think the largest uncertainty is actually from the neutron lifetime and not from the baryon photon ratio, if I remember correctly.
That's true, but again, it's not an open.
Yeah, in the same. So this is something actually I'm having my student look at is because there is this discrepancy in the neutron lifetime, how does that propagate into these? Okay, so hopefully you can start to see where I'm going here. So these are the two things that I can modify. So how can I modify this? I can modify this with new physics. So let's move on to some new physics. Actually, so before I go into that though, I want to, so these are kind of general expressions.
Just by changing the couple.
You could also change it that's different. So in a,
That's the main thing that people think about now.
yes,
Okay.
yeah. So in our first paper, that's effectively what we did. When I write down the model, you'll see. So the first paper was looking at a universally coupled scalar, which is just making g mu nu into g mu nu times e to the phi squared. And that could be repackaged as just changing Hubble by changing frames. But in what I'll do today is I'll have different couplings to different parts of the standard model. Okay, so first, before I start telling you about the model, I want to dig into what these two objects are and seeing what parameters I modify when I say I'm changing the neutron abundance and I'm changing the neutron decay. It's much slower on the blackboard than slower paced. I'm also not able to write super fast. Okay, so let's first look at the neutron abundance. So first approximation, this neutron abundance was given by the expression I had before, minus. So now I'm going to call M and P the neutron proton mass difference, so I don't have to write as much. And this was at the weak, what I'm calling the weak freeze-out time. So this is an approximate temperature at which the weak interactions freeze out. So if I then want to see, okay, how can I modify this? I just do some variations on this object, and you get that delta x and w over x and w depends on n and p over t weak. And then what can I modify? I can change the neutron proton mass difference. Okay, so delta MNP over MNP. Or I can change the temperature at which the weak interactions freeze out with respect to Hubble. Okay, so this is what I'm calling the instantaneous approximation. However, it turns out that this is, it's an okay approximation, but one can do better by actually looking at the full kinematic decoupling of the weak interaction. So remember, it doesn't happen instantaneously. It happens over some period of time. So to calculate that, I think I changed notation, so apologies. So we have the neutron abundance, which we can call n over nb, so number of neutrons over baryons. It's given by 1 over 1 plus e to the m and p over t. I'm going to call this the, and this is the thermal abundance, equilibrium abundance. So xn equilibrium. So thermal equilibrium abundance. Okay. How does this evolve? It evolves with a kinetic equation, which is given by dxn dt. So how does xn evolve? Depends on this kind of neutron-proton, the weak interactions, times 1 plus e to the minus m n p over t, times xn minus xn equilibrium. Okay. Where, do I need to write this down? These are the weak interactions. Live here. Okay. Probably should have written it down. So if you go and then solve these equations and set your time to be at weak freeze out, you get an equivalent, kind of the analog of this expression, so x and w. But now it's a bit more complicated. So I have to integrate dA over a. There's a minus sign. dxn equilibrium over dA. And an exponential piece. Minus a to infinity dA prime over a prime. Lambda n p over h a prime 1 plus e to the minus n p over t. Okay, so a bit more complicated than this simple exponential. Then we can do the same exercise, which is to perturb this, so vary this. And you get quite a long expression, which I will write down, so give me some, if you would be a little patient. Might take me some time to write down. Okay, so I want to perturb this now. So delta x and w over x and w. And this has many terms in it now. It's not just the two pieces up here. So what do we have? We have 0 to infinity dA over a, m and p over 2t, 1 plus cosh, m and p over t, okay. An exponential of minus a to infinity a prime over a prime lambda n p tilde. Okay, so I'm defining just to make life a little simpler. This tilde is the integrand here. Okay. Now this is all multiplying. Minus lambda n p tilde. So the integrand of the exponential. M and p over m and p. So okay, again we see that it depends on modifications to the neutron-proton mass difference. Plus integral from a to infinity. dA prime over a prime, lambda np tilde, m and p over t, x and equilibrium. Another piece that depends on the neutron-proton mass difference. A piece that is basically modifying the weak interactions. So GAN squared over 1 plus 3 GAN squared modifications to the weak axial coupling. Can change G Fermi. Some term. This is just a phase space factor, this J. Another piece that depends on the neutron-proton mass difference. So you start to see the neutron-proton mass difference is a key player here. Plus 3 with zeta function. That's 2J. Mass of the electron now shows up. And so we are sensitive to changes in the mass of the electron. And again, the neutron-proton mass difference. I think I lost the bracket somewhere. Let's see. All of these are in this this piece here. Okay, so what do we have? We have modifications to the neutron-proton mass difference, modifications to coupling, like axial coupling, modifications to the Fermi constant, and modifications to the electron mass.
Do you include also the modification of the deuteron binding?
Yeah, so that's coming next. Very good. So this was at what I'm calling the weak freeze out. But again, we have neutron decay. So BBN is kind of occurring in this period between weak freeze out and what I'm calling BBN, which is when the deuterium bottleneck ends. And so I'm going to define X and BBN to be X and W. So this the abundance at weak freeze out, and then take into account the fact that the neutrons are decaying. So I'm going from minus A weak to A BBN, BA over A, H gamma N. Right, this is the neutron decay. So I go and then perturb this guy. So it's a lot of perturbing. We'll get to the punchline soon-ish. So if I perturb this, this depends on delta X and W over X and W, which I won't rewrite, but it's this beautiful expression here. Minus A weak over A to A BBN, BA over AH, modifications to the neutron decay, minus gamma N over H, evaluated at A BBN, times the modifications to the temperature at which BBN ends. And it turns out that this is equal to changing the modifications to the deuterium binding energy. Because I'm defining this to be when the deuterium bottleneck ends. What does the deuterium bottleneck depend? It depends on the binding energy of deuterium. Because it's defined as when the background photons are not energetic enough to break up deuterium. So if you can go through and work this out, that this temperature, modifications to the temperature at which BBN ends is directly related to any modifications I make to the deuterium binding energy. Okay.
Sorry, so delta gamma N is like an overall rate, it's like this factor in front, because then stuff like GA must occur inside there.
Yeah, so this, trying to decide if I want to write it all out. Maybe I'll just say, so this depends on delta GA over GA, delta GF, delta ME over ME, and delta MNP over MNP. Okay. So the only new thing that has popped up actually is the deuterium binding energy from this. All of this expression here is actually coming from basically the same interaction that's driving this. Okay, so if I wanted to combine everything together, which was the changes in delta YP over YP, remember had a piece that goes like xn BBN, or xn BBN, and a piece that depended on the neutron decay, which is encoded here. Just won't write it out. And then we want to compare this to that number that I wrote down before, so 0.008 plus or minus 0.0112. Okay, so these are the modifications that I'm interested in looking at. So how do I modify them? I can modify them with new physics. And so the particular model that I want to look at is in the title. It's an ultralight scalar, which has its own problems, but just kind of curious to see how things will be modified. Okay, let's see. I think I'll leave up this expression here. Okay, so I'm going to look at the following model, parameterized in the following way. Oops. So I have a light scalar that's quadratically coupled, so phi squared, m Planck squared, and it couples to the standard model the following way. So I have a coupling to photons, basically modifications to E, f mu nu, f mu nu. The coupling is related to what I'm calling this D sub E. The superscript 2 is indicating that it's a quadratically coupled guy. There's been a lot of work looking at the linearly coupled one. That's a dilaton. So that would have a 1 up here. It can also couple to the gluons. 2, 3, 3. I also want to couple it to electrons. So I have DME2, ME, E bar E. And to the light quarks, so up and down. To get DMI2 plus gamma MI. DG of 2, MI psi bar psi I. Okay. So in the literature, there's a few ways that people parameterize this. This is one that's from Damore and Donahue that I liked to look at. Okay, so now that we've written this down, I can then ask, how do this, in particular this parameter, these D's, enter into these modifications of the various parameters that enter BBN? So you can go and work that out. So one of the easiest ones is fine structure constant. Gets modified by this DE of 2 over 2, I think.
So GG tilde is not relevant.
Sorry?
GG tilde.
GG tilde is not
I'm asking.
relevant because I have a phi squared, which is even, parity even. Right, GG tilde, you would need a pseudo scalar. So yeah, so if it was a linear case, I could look at like an axion-like particle, and then I would have a GG tilde. For just a scalar, I would only have the GG.
So you're assuming CP is conserved, I guess?
Yeah, in this case, I'm assuming. I guess, Mariangela, you looked at the axion, basically axions and how they would modify BBN several years ago as well.
Sorry, why is it happening to the light quarks only, or?
So this is at low energy. Yeah, so I've decoupled all the rest, right? Because I'm at MEV scales.
And these other factors, are they going to make like a normalization group invariance or something like that?
Yeah, so this is the anomalous dimension.
Yeah, and I guess the beta function doesn't.
And the beta function shows up. Yeah, it shows up here.
Okay.
Okay, so let's look at the change in the fine structure constant. It goes like phi squared over 2, where this phi is defined to be. I've just rescaled my. One of them is script, and I guess this is the script phi, my non-script phi by Planck. Okay. You can also change the QCD, lambda QCD. And as you would expect, it depends on the coupling to GG. So dg2 phi squared over 2. I can change all of the fermion masses that we see here. So we have delta m f over m f equals d m I 2 over 2 phi squared over 2. Then we have 3 more. So we have, remember, the neutron-proton mass difference showed up quite a lot. So this will also modify that. Time, okay. And P. It depends on just some proportionality constant, alpha lambda QCD over M and P. And then it depends on this coupling. Depends on this one. That's dg of 2. So couplings to photons, couplings to gluons, phi squared over 2, plus the couplings to the light quarks over M and P. So mass difference between down and up, d delta M of 2 plus gamma dg of 2 times phi squared over 2. And this delta M of 2, so for the light quarks, you can have either the symmetric or asymmetric combination of the masses. And for BBN, it's only the asymmetric piece that really, that matters. Okay, and then we need modifications to the deuterium binding energy. So this goes like 18 Eg2 phi squared over 2. And then the last one is G Fermi, which is related to this one. Of 2 phi squared over 2. Okay.
Sorry.
Yeah.
So one question for the proton-neutron mass difference. If you start from the quark and the gluon couplings, is there also some uncertainty in the form factor that you find about?
So this, yeah, so this expression, there's a piece that comes from the ENM contributions, and then a piece that comes from the light quarks, and the coefficients in front of each of those pieces we get from lattice simulations. And there is some error with that. But because we're looking at shifts to that, I think everything kind of scales in the same way. Okay.
Sorry, can I ask another
Yeah.
Sorry. Why does the binding energy of the neutron doesn't depend on the DMI? Doesn't the binding of neutron depend on this binding between the pi mass and the distance cap?
Yeah, so I think there's a few ways to parameterize this. So this one is looking at how lambda QCD, effectively this dg is coming from how you change lambda QCD here. And this is coming from, actually, I think from the strange quark mass. Yeah, so there's one way by looking at like the strange quark, there's another by looking at the mesons. And what we found was it doesn't make a difference. At least in the universally coupled case, it didn't make a difference which procedure you picked. But actually a good point. For this case, it might matter more. But this one. So this so there's a lot of work by like Alain Koch and where they go. What they're interested in is just changing fundamental constants in BBN, and so they have these long papers going through those. And so yeah, you get this factor of 18 because of some of those calculations.
It's like sensitive to
Yeah, it's sensitive, but it's very complicated. I mean, it's not really nuclear that you understand them in terms of exchange of pi.
Yeah, I think this is a quite tricky.
The potential is very complicated, so I was surprised. 18 is just unexplained.
You're saying that it's such a nice number. It doesn't have decimal points behind it. Yeah, there's some properties though. Like so, in the universally coupled case, you need everything that's mass dimension 1 to scale the same. And so in that sense, you can kind of see where these various numbers come. So you look at all the different contributions to delta BD.
I think it's also goes deeper on since it's fine-tuned, yes, you don't need to know the details of the program.
No, you don't need to know the details to compute the production of neutron. But to do the binding agent to solve this. But maybe it's more deviation in the two calculations.
I think you can do some basic FTs and it depends on one shot.
But it's the input is precisely that is lose the bound. So
yeah, that's true.
That's true.
Yeah, so I think there's there's a few different ways to calculate these, and people know how to, people who have thought about this more than I have, know how to do it. Okay, so now we have this scalar. So also in the title, I wanted the scalar to be dark matter, so that sets one boundary condition for the size of the amplitude. So I want today for this phi squared to populate the dark matter, but what I'm interested in is the effect of this phi at BBN. So I need to understand what is the size of the field at BBN, and to do that, I need to evolve it backwards in time. And to do that, I do my some familiar equations. So get the evolution of phi, which phi dot plus v prime of phi equals to 0. Okay. Yeah.
So why does the scalar need to be ultralight?
It doesn't need to be ultralight, but you get no effect when it's heavy. Yeah. I'll draw a cartoon of the constraint, and you'll see the constraint weakens. Yeah. Okay, so here's the evolution equation. So phi double dot plus a Hubble friction term plus a potential term. So a priori, this potential is 1/2 m phi squared phi squared. This is where things get kind of ugly that I'm going to sweep under the rug. So we have, in principle, this potential of the mass. However, because I'm looking at this quadratically coupled, which I don't say here, quadratically coupled guy, there'll be a back reaction. Sorry, I keep losing a back reaction on the mass of the scalar from the standard model. Right? We have this phi squared, so all of this stuff is also going to give you an effective mass. So instead, I have an effective mass, phi squared, where this is a combination of the bare mass, m phi, plus whatever is induced by this back reaction. So then to calculate the evolution of this scalar, I need to also understand how this induced mass evolves in time, and it turns out to be can be quite complicated depending on the coupling. So I'll just take one example, which is the electron coupling. And so the induced mass, so this is the scalar, comes from something like this, coupling like that. So it's like the thermal mass. And I won't go through the derivation, but you end up with that the effective mass is the bare mass plus 4 pi d m e. So it depends on this term, the Lagrangian, over m Planck squared times the trace of the stress energy tensor of the electrons. And so what is this? This is the pressure, the density of the electrons plus 3 times p, the pressure. And this we can get from other things. We also go through and work through the case of the photon coupling, which is a bit more complicated. Do I have time? No, yeah. If you want to look at those, we can talk offline.
Is there also a quartic coupling?
There is a quartic coupling. So this is something actually Tom just sent me this morning, like an induced quartic coupling. And when I draw the plot, I'll show you where he says it is. I don't know if I believe it quite yet. So this is my graduate.
Shouldn't I expect it must be small? Shouldn't I expect that connection to be small compared to the bare mass, or not?
No, not necessarily. Yeah. So yeah, it's good. So this is a good point. So depending on where I am in time, the evolution will be quite different. So at early times, this term dominates, so it's flat. It's dominated by a Hubble friction. At late times, I want the bare mass term to dominate. I want it to oscillate, so it's going to be oscillating. But there's this intermediate regime where this term could be the one that dominates, and then you get a kind of more interesting behavior, depending on how you want to call it. Is the thermal mass, yeah. And so for the electron case, it's not too bad. For the photon case, we haven't quite figured out how to do because it's a two-loop calculation. So right now we're doing a high temperature limit and a low temperature limit. Okay, so now that we have this, so thanks Deepan for asking the question, we can then evolve it back in time, but depending on which era we are in, the phi field will have different evolution. But at the end of the day, we get what is the amplitude of phi squared at BBN, plug that into these expressions, which then I plug into what I had on the board before, and we see how much do I modify the helium for abundance. I say it has to be less than the difference between the theoretical prediction and the observed value, and then so I can get a constraint on this. So it's always fun to draw a constraint plot on the board because it's usually not very accurate, but hopefully it gives you a sense for what we're talking about here. So I have m phi here in EV, and this is going to be d. First, I decided to do the photon case, even though I didn't. They're pretty similar. Okay, and the coupling here. This is about 0.1. So m Planck is around here somewhere, and so these scalars we're not the only people to think about ultralight scalars. So there's a lot of other constraints on these guys. So for example, you have constraints from superradiance, which are around like 10 to the minus 18 and 10 to the minus 13, which have kind of this shape here. Okay, so this is superradiance. We cut off these plots here because once you're above this coupling, let's say there's some accretion disk around the black hole, the scalar will get an induced mass from that accretion disk, and this may modify the dynamics of superradiance. So I don't know what happens. I have to ask Masha what happens. So I have like kind of a little ignorance band here. You also have kind of like the experiment microscope, which is a equivalence principle test up in space, which looks something like this. This is microscope. We have the Ayotte wash experiment, which is a torsion pendulum. And what's kind of interesting now about these quadratically coupled cases is you get Earth screening effects. So you actually get much stronger constraints if you go out into space. And so with Ayotte wash, you have something that looks like this, and then you kind of lose sensitivity here because of these Earth screening effects. We have structure constraints that show up about 10 to the minus 21, like Lyman alpha, minus 21. They look like this. Okay. And then so the BBN constraints look something like, let's see where to, like this. And then you get some wiggly stuff. And something like, actually I think they go lower, like that. Okay, so this would be BBN constraints. Very much a cartoon. You get kind of, actually this should be over here. You get kind of this weird wiggly behavior here. Because it turns out when you do the full kinematic decoupling rather than the instantaneous decoupling, there were terms that came in with opposite signs in that expression, and you get some weird cancellations, and so you have more structure in this region. This mass scale.
Yeah.
So this is really where Hubble is dominating. Up here you have the bare mass that's dominating. And yeah, and this is that intermediate regime where the induced mass is playing the main role. Okay.
Do you have constraint from CMB also?
On CMB, do not. Are there constraints from CMB?
You can change the scattering rate.
Actually, no. There are constraints from like changing the Thomson scattering, and I believe those are actually weaker than. So this is like changing the fine structure constant or the electron mass, and those are quite a bit weaker than the BBN bounds. And I believe, I don't remember in this parameterization, but it's somewhere. I think it might even be weaker than AO-wash experiments. And so part of the reason, I mean, you would kind of expect it to be weaker than BBN because the field values are so much larger at BBN. And this is one reason why BBN is, in some sense, a very powerful probe, is even if the field values are, the amplitudes are small now, they could have been very large at BBN and had a large effect there. There's one thing that I haven't, so maybe I'll mention it, because nobody's brought it up. At some point, this phi squared over, so I can reparameterize this coupling over m Planck phi squared into a phi squared over an effective scale squared. So basically phi squared over lambda squared. And I'm looking at kind of behind the scenes here expansions in this term. So at some point this is going to be order 1, and it turns out it's something like this. And so the punchline then is I wouldn't trust what we've done above this, because here you need to start specifying what the UV model, like what is setting this operator above this dashed line where we become non-perturbative. So that could be a fun exercise for our model building aficionados in the room. Okay, so I think I'll stop there. If you want to see a more proper plot, not this scribbly cartoon, I have them on my computer.
So if you have phi instead of phi squared, it's completely different?
Yeah, it's completely different. The reason why we don't look at phi, because there you have a long-range force, and the fifth force experiments are quite strong. Because there it goes like 1 over r, the potential goes like 1 over r. Here you get this 1 over r cubed, and so that buys you a little bit. And the other thing that's really different is you don't have this back reaction. So in some sense it's a simpler process, but it's also very much ruled out in the regions that BBN could probe.
And people have done this for action like particles.
Yeah, I know. Yeah, the linear with the CP odd. Mariangela did in 2014 or something. Yeah.
So let's thank our speakers.